Okay, welcome back to the second part of lecture 10. And now we're going to prove the Perron-Frobenius theorem. Okay, so, all right. So first we start with Perron's theorem. Okay, so suppose that A is a positive matrix, right? So remember, a positive matrix, all its entries are positive. So in this case, the following four things will hold. Okay, so if you remember, rho of A is the spectral radius of A, right? So it turns out that rho of A will be an eigenvalue. And this eigenvalue has a strictly positive eigenvector. Okay, so the eigenvector corresponding to rho A has all entries positive. Okay. So now rho of A is the only eigenvalue in the complex circle. If you take the circle like, all the complex numbers lambda such that the absolute value of lambda is equal to rho of A is the only eigenvalue there. Okay, which means that is the only eigenvalue of maximum absolute value, right? So that's what 2 says. So 2 says that rho of A is the only eigenvalue of max absolute value. Now, and 3 and 4 is just saying that actually rho of A has geometric multiplicity 1. Okay, so you only have one eigenvector corresponding to this rho of A, and rho of A has algebraic multiplicity 1. Okay, so all right. And today we're just going to prove like parts 1, 2, 3. But if you want to see like the proof of 4 as well, you can look at the references where I learned this proof from as well. Okay, so all right. Now let's prove 1, right? So by the definition of rho of A, we know that there is an eigenvalue lambda such that the absolute value of lambda is equal to rho of A, right? Because if you remember, what was the definition of rho of A? Rho of A is exactly the max overall lambda eigenvalue of A of the absolute value of lambda. So by definition of rho of A, there is an eigenvalue with this absolute value, correct? Equal to rho of A. So then let V be a corresponding eigenvector, right? So to each eigenvalue, we have one eigenvector. Now, here's the thing. We're going to define U to be the vector given by, take every coordinate of your eigenvector and make it the norm of that entry. Does that make sense? So V is a complex vector, but now we're taking U to be a real vector, right? So U here is just like each entry of U is the absolute value of the corresponding entry of V. Okay, great. So now what do we have? Well, let's compute the ith entry of this matrix here, right? So if I take the ith entry, what do I do? Well, when I multiply by A by U, and I want the ith entry, essentially what I'm doing is I'm taking the ith row of A and multiplying by U, right? Doing the inner product. And that's why we get this sum here, right? Because this is the inner product of the ith row of A with U, right? And then now here's the thing, but we know that UJ, what is UJ, right? Well, UJ, this is essentially the same as saying this is sum of AIJ times the norm of VJ. By definition, right? But we also know that the AIJ, they are non-negative, right? So in particular, this is equal to the sum of AIJ VJ, right? So then by the triangle inequality, the sum of the norms is bigger than or equal than the norm of the sum, correct? So this inequality here is just by the triangle inequality. Right? And now, but if you look at what is inside of the absolute value, what is this? This is exactly the ith entry of A times V. Does that make sense? Like this part here is exactly A times V, and I take the ith entry. Yeah. But the thing is, if you notice, well, what is the ith entry of A times V? Well, V is an eigenvector. So the ith entry of A times V is exactly lambda times Vi. Right? But lambda times Vi, if I take the absolute values, what do I get? This is exactly equal to, well, the absolute value of lambda is rho of A, and the absolute value of Vi is equal to Ui. Correct? Is it too fast? Should I write on another page, or are you good? Okay, so all right. So then we have this inequality for every coordinate. So what did we just prove? We just proved that if I take this vector u that we defined, we know that A times u is greater than or equal than rho of A times u. Right? All right. So then here's the thing, right? So we just proved that A times u is greater or equal than rho of A times u. And every time you see this, something is greater or equal than the spectral radius, you should think, okay, this must be equal by the definition of the spectral radius, right? But let's prove that, right? So how do we prove? Suppose that this inequality here is actually strict. So if the inequality being strict, what do we mean? Is that like here, we're going to assume now that A of u is bigger than rho of A times u, right? If you know the variational definition of eigenvalues, you know that this cannot happen, right? So you know that this, like, you already know it should be equal. But suppose that you don't know that. Let's just prove that, supposing that you don't know that, right? So let's assume that this inequality is strict. Then what we have is that let's just multiply this inequality again by A on both sides. And we can multiply by A because A is positive, right? So if you have this inequality, it will still remain bigger. Does that make sense? Because the vectors are big, right? Like, so I can multiply on both sides and I get that A squared times U is bigger than rho of A times AU. And now you should think of this as A squared times U as A times U. Okay, so this is the vector, right? Now the thing is, remember, we have that the vector A times U is bigger than rho of A times U, right? So now we can use the positivity lemma to show that there is some positive epsilon such that A squared times U, right? Because here's the thing, right? Like we have that AU is a vector, and this is bigger than rho of A times U. Now the inequality that we have here, once we multiply by A, this means what? That A times AU will be bigger by the positivity lemma than A times rho of AU. Correct? But moreover, we also know that there is a 1 plus epsilon that we can add in here. We can throw in a 1 plus epsilon here, right? And we can leave it positive, or we can say, okay, greater or equal, right? Doesn't matter, right? Okay, great. So we know that there's a positive epsilon such that this holds, right? Okay, but now if you notice, by induction, what can we say? By induction, we can just prove that A to the n times U is greater than or equal than 1 plus epsilon to the n. Oh, sorry, there's an n plus 1 here. A to the n plus 1 is greater or equal than 1 plus epsilon to the n times rho of A to the n times A times U, right? Just by induction on this like formula here, right? Because every time I multiply by A, I'm picking up an extra 1 plus epsilon, right? Okay, so All right, so we can prove this. And now, by Gelfand's formula, what do we have? Let's look at Gelfand's formula. So we know that rho of A is the limit of A to the n, like the Frobenius norm of A to the n, like to the power of 1 over n. But we know that this norm has to be greater than or equal than 1 plus epsilon times rho of A, because, you know, when I take this like A to the n times u here, right, I'm getting exactly that this is like this inequality holds, right? So then in particular, we know that, you know, this rho of A is greater or equal than, so the Frobenius norm of A to the n, okay, is greater than or equal than 1 plus epsilon. And here we're going to do like n minus 1 times rho of A n minus 1, but n is going to infinity, so n and n minus 1 are pretty much the same thing. But then I have to take the 1 over n power, right? So in particular, what happens here is that like this is greater or equal than 1 plus epsilon times rho of A. But then we just proved that rho of A is greater or equal than 1 plus a positive number times rho of A.
You know, why is it n minus 1 instead of n?
It's just because by induction here, we're proving that like A squared u is greater or equal than 1 plus epsilon times rho. So once you multiply again, you're going to pick up like A cubed of u is greater or equal than 1 plus epsilon squared times rho of A squared.
Okay. Right. So the second line should be A raised to n plus 1.
Yeah, there's the n minus 1 here. Like, let me put n minus 1 here. Yeah. Sorry, yeah, it's just like backwards compatible here. Yeah. Okay. So then this is a contradiction, right? Because we just proved now that like rho of A is bigger than 1 plus epsilon times itself. And this cannot happen, right? Because rho of A is positive. Okay. So in particular, what does it mean? Well, it means if we reach the contradiction, it means that whatever our assumption that we made was wrong. So the inequality cannot be strict, right? So this proves that here we just prove that A times U is equal to rho of A times U. But if this holds, what did we prove? We just proved now that there is an eigenvalue of value rho of A, right? With a positive eigenvector, right? So now let's finish the proof. So we just proved that rho of A is an eigenvalue, and it has this eigenvector U, which is non-negative. All we know is that U is non-negative, because remember, how did we define U? It was each coordinate is the absolute value of that original eigenvector, right? So, okay, so we have this, but now let's prove actually that U is positive. So all the entries are positive. So why is U positive? Okay, now, if you remember, if I compute like A, maybe let me not write in red. If I compute A times U, we know that this is equal to rho of A times U. So in particular, if I look at the ith coordinate, right? What is the ith coordinate? Let's look at AU and let's look at its ith coordinate is equal to the sum of ij going from 1 up to n of aij times uj. But the thing is, if you remember, our matrix is positive, right? So this quantity, so it will not, and we know that the spectral radius is positive, right? So we know that this eigenvector u is different from 0. So all we know is that u is different from 0, right? So then if u is different from 0, there is one entry, right? So this is greater or equal than, let's say, aik uk, and this uk is bigger than 0. And we know that our matrix is positive, so this is also bigger than 0. So we know that this is bigger than 0. Does that make sense? Yeah. And that is just because our matrix is fully positive, right? So we have that all of the coordinates of AUI are positive. But now AUI is equal to rho of A times UI because it's an eigenvalue, because rho of A is an eigenvalue. right? So in particular, we know that ui is positive. And this holds for every I. Does that make sense? Okay, excellent. So now we just proved that U is positive, right? So now we're ready to prove item 2, right? Like we just proved item 1, that rho of A is an eigenvalue, and there's a positive eigenvector for it. Now let's prove item 2, which is the only eigenvalue on the complex circle is rho of A. So this is the only eigenvalue of largest magnitude, right? How do we prove this? If we had another eigenvalue, lambda, which is different from rho of A, and suppose it is in this circle, right? Like the circle of all complex numbers mu, such that the absolute value of mu is equal to rho of A. Okay. Now, suppose that z is the eigenvalue, is the eigenvector. Sorry for the typo here. This is eigenvector corresponding to lambda. Okay, so by the previous slide, right, by the same argument that we did for item 1, we know that if we define w as wi equal to the absolute value of zi, we actually know that a times w is equal to rho of A times w, right? This is just what we proved in the previous slide, right? This holds for any eigenvalue which had absolute value equal to rho of A, right? But if we look at this equality again, if we look at this equality that we proved, like let's just write it out. So if we have, in particular, like if this is true, it must be the case that like AW, like the ith index of W is equal to rho of A times WI, right? Like for all I. Just because the vectors are the same, so all their coordinates must be the same. Yeah. So now let's just write out what this means, like this equality here. And this equality is equivalent to saying, if I compute on the left A times W, just the ith coordinate, it's exactly the sum over all indices J of Aij times Wj. But this is equal to rho of A times the absolute value of Zi, which is exactly this guy on the right here, right? But now, if you think about it, like rho of A times Zi, rho of A is the absolute value of lambda. So I can pull in rho of A inside of the absolute value, and this is equal, right? So this is because lambda, absolute value of lambda is rho of A, and absolute values are multiplicative. Now, what is lambda times Zi? If you remember, lambda times Zi is exactly equal, because lambda is an eigenvalue, lambda eigenvalue and z eigenvector, right? Like the corresponding eigenvector is exactly the same as the sum of Aij times Zj, right? Because this equality just follows from the fact that A times Z is equal to lambda Z. Right? Okay. So, and this follows for every index I, right? So for each index I, so for each coordinate, we have that this holds, right? And now here comes a lemma that is not hard to prove, but it's a bit nothing super illuminating. So if these conditions hold that we have here, like if these conditions hold, like from this equation, okay? So then there exists a complex number alpha, which is non-zero, such that if I multiply alpha, okay, a complex number alpha, by the entire vector z, then I have that alpha times z is a real vector and is greater or equal to 0 and is non-negative, okay? So what is this lemma saying? This lemma is saying that if you think about the complex numbers, like if your eigenvector satisfy these conditions, it must be the case that they are like all complex numbers with the same phase, right? Like the complex angle of all the entries are the same. So you multiply by alpha, you put them all back to non-negative reals. Okay. So, and the proof is really not hard, but you can just square both sides of the right-hand side here, and then you can use complex conjugates and you get that. Okay, so like if you want to see the proof, like the details in the notes that I reference. Okay, so all right, so now we know that there's this complex alpha such that alpha times z is greater or equal to 0, right? But now if alpha times z is greater than or equal to 0 as a vector and is also a non-zero vector, right? Because my eigenvector is not the trivial one, right? It cannot be trivial because lambda is not 0.
Yeah.
Yeah.
In the last slide, you meant that every like zi has the same phase. Right?
Every zi has the same phase, exactly.
Okay.
Yeah. So now we have that alpha times z is greater or equal to 0 and is non-zero vector, right? Because it corresponds to a non-zero eigenvalue. So it cannot be the 0 vector. So we have what? We have the lambda times alpha times z is equal to, remember, alpha is a scalar and lambda is also a scalar, right? So they commute. So this is equal to alpha times lambda times z. But lambda times z, because z is an eigenvector, lambda times z is equal to a times z. But a times z now, remember, alpha is a scalar, a is a matrix, so we can swap them. So this is equal to a times alpha z. But remember, alpha z is greater or equal to 0, and a is a positive matrix. So I'm multiplying a positive matrix by a vector which is non-zero, which is greater or equal to 0, all its entries, which means that this new vector has to be also greater or equal to 0. Does that make sense? So, okay, so now what did we prove, right? So we just proved that lambda has to be a non-negative number, right? Because here I'm multiplying like a non-negative, I'm multiplying a complex number lambda by alpha times z. But remember, alpha times z is a real number, right? Like, so every entry of alpha times z, let's say, if I multiply alpha times z1, let's say that z1 is different from 0, right? So we know that alpha times z1, this is non-negative. And we just proved that this also has to be greater or equal to 0 and real. The only way that this can happen is if lambda, well, there's one of them that's different from 0, right? So we have that this is like bigger than 0, and we're saying that this is greater or equal to 0. The only way that this can happen is if lambda is greater or equal to 0, right? So we just proved that lambda is a non-negative number. But the thing is, if you look at the complex disk, what is the only non-negative number in this circle? The only non-negative number in your circle is exactly rho of A, right? So this proves that, okay, the only eigenvalue in the complex circle has to be rho of A, right? So in particular, all the other eigenvalues must have smaller absolute values, strictly smaller absolute value. Okay? So this proves 2. Now, let's just prove 3. The geometric multiplicity of rho of A is 1, right? So, all right. So suppose that it is not 1, right? And let's say that we have 2, like, so if it's not 1, we know that we have actually 2 eigenvectors corresponding to rho of A. Does that make sense? Right? Just because of the assumption, right? Because if my geometric multiplicity was 2, I could have had 2 linearly independent eigenvectors for rho of A, right? Just by definition, right? We're assuming that our geometric multiplicity is 2. Now, we can assume that both u and v are real vectors. And why is that? So this is because our matrix is real, right? Like, so if I had like A times like a complex vector, which I can write it as like, let's say, like phi plus I psi, where phi and psi are real vectors. Well, this is going to be like rho of A, which is a real number, times phi plus I times rho of A times psi. Right? So if I just compare the real parts, like phi is an eigenvector, and psi is also an eigenvector, right? So that's why we can assume that both of them are real vectors. Okay. And now, if we have, we have, they're both real vectors. Now let beta be a positive number such that u minus beta v is greater or equal to 0. And at least one entry is 0. Okay. So we can always choose this beta, right? So, okay, because we know that we know that rho of A. So why can we do that? Because we know the rho of A has one eigenvector with all positive entries, right? So we take U to be this eigenvector with all positive entries and take V to be the other eigenvector, any other eigenvector. So then I can scale B so that all its entries are like smaller than the corresponding entries of U, right? Okay, and we know, and we're going to choose beta. We can also choose beta so that at least one entry is 0, right? We can always do that. So, all right. Now, we also know that u minus beta v will be a non-zero vector because the vectors are linearly independent, right? So that's our assumption. Okay, but now if you notice, for each index between 1 and n, if you look at rho of A times this index, we know that this is equal to A times this vector here, like u minus beta v, right? The ith coordinate of this vector. But we know that this, remember, this is a positive, like this guy is strictly positive, right? Because remember, I'm multiplying a positive matrix by a non-negative vector, right? So this is a non-negative vector, this is a positive matrix. So I'm always going to get a positive number. And this is non-zero, sorry, yeah, this is non-zero, right? By the same argument that we've been doing so far. So in particular, this cannot happen, right? Because this contradicts our choice of beta. Because this holds, this inequality, this strict inequality holds for every index I. But we chose beta so that there is at least one entry which is 0. So we're proving that 0 is bigger than 0. That's not true, right? So this contradiction shows that we cannot have two linearly independent eigenvectors. Okay, so the geometric multiplicity of A is 1. Okay, so all right, and so for item 4, you can just see the notes. I just wanted to give you a glimpse of all of this, and this is really kind of, those 3 parts are really the most important ones for us. Okay, so all right, now well, okay, we need algebraic multiplicity 1 as well, but like anyways, but you can see in the notes. All right, so now we're ready to prove the Perron-Frobenius theorem, because now remember, we proved Perron's theorem for positive matrices. We assumed that A was fully positive, right? But Perron-Frobenius holds for any non-negative matrix, okay? So your matrix has to be non-negative. That's a difference. But also, if it's non-negative, we have to assume that it's aperiodic and irreducible, okay? So if we have that our matrix is aperiodic and irreducible, and you know the definition of aperiodic and irreducible based on the Markov chain definition, it's exactly the same definitions as the Markov chain one. Okay. So now, if this matrix is aperiodic and irreducible, then the following holds, right? The same conclusions hold. Right? So rho of A is an eigenvalue. It has a strictly positive eigenvector. Rho of A is the only eigenvector of largest magnitude, and it has geometric multiplicity and algebraic multiplicity 1. Now, how do we prove this? Right? The proof is quite simple. It's simply, well, all right, if you remember from previous lecture, we saw that a matrix A being aperiodic and irreducible implies that there exists a power m such that A to the power m has all positive entries, right? So that was the lemma from previous class. And then, well, okay, just take this power A to the m, and just note that we can apply Perron's theorem to A to the m, and note that the eigenvalues of A to the m are just lambda I to the m, where lambda I are the eigenvalues of A, right? So, and since we're always talking about just the magnitude of the largest absolute value, this whole thing, I can just take the square root of m anyways, and it doesn't matter, right? Like the conclusions hold for A.
Do you need irreducibility here for that statement, or just
Sorry?
like if the matrix is just aperiodic, then also there should exist M, right? Such that AM has all positive entries.
Yes, but then if you're not irreducible, you could have more like eigenvalues, right? Remember the same thing that like I can have more eigenvalues because I can have just like direct sums of things, right? If you're talking about uniqueness, like the geometric multiplicity one and algebraic multiplicity one, you need the irreducible.
Okay, I see.
And also
So,
even 2, right? Because 2, you would have rho of A could be like, there could be many eigenvalues in the complex circle, or the multiplicity of A would be bigger, right? So each irreducible component will give you like one of these rho of A's, right?
so if I understood correctly, like aperiodic is like the diagonal entries are non-zero, and irreducible is like the off diagonal entries are non-zero.
No, no.
Oh,
It's much more complex than that, right? Like aperiodic just means that like aperiodic just means that if you look at the directed graph, like, and you look at all the paths that you have from one vertex to another, like the GCD of all of those paths, like they're going to be 1.
yeah. So I'm saying there exists M such that A raised to M has positive diagonal entries.
Right. No, positive, all entries are positive.
No, just aperiodic, I'm saying. So suppose the matrix is only aperiodic, then is it true that there exists M such that A raised to M has all positive, the diagonal entries of A raised to M are all positive? Because it's like you're going back, right? If you just take M to be the GCD, then you're going back. There's like a path going back to the.
So I'm not sure that is true. So because you can have periodic matrices with the diagonals positive, right? Like, oh, sorry, no, periodic matrices. So for example, if you have if you have the matrix like 1 goes to 2, 2 goes to 1. So that is periodic, right? Because I only go back and forth. Like I only go back and forth like every twice. Like, yeah, it's not true, right? Because if you look at the matrix 0, 1, 1, 0, this is just the graph, like 1 goes to 2, 2 goes to 1.
Yeah.
This is clearly bipartite, so it's periodic. But then if you do 2 things, you have the identity in the diagonal, right? So like that's not true, that aperiodic is a power gives you the positive in the diagonal. Right, you need the GCD.
I have to think about it. Yeah.
Okay, but just look at this example. Yeah, so this is the example, the counter example to your claim. Okay, so all right, so now we know that by the previous lecture we saw that, okay, A being aperiodic and irreducible implies there is this M. So now we reduce this to Perron's theorem, and then we can conclude here, right? So okay, so that's Perron-Frobenius, and this concludes the second part. Now we'll go to the applications, right?